Welcome to Q Point. This is a platform to discuss some selected topics related to electronics and communication engineering. The discussion is in the undergraduate level. The topics of discussion include analog circuits, digital circuits, network analysis, analog and digital communication, signal systems and signal processing, microprocessors, etc. The current lecture is on analog circuits. First, we discuss the inverting amplifier. Before entering into the topic, let us see the conventions used in this lecture. You know, a voltage is a measure of the potential difference between 2 points. So, it is represented with two subscripts. If only one subscript is used in a particular representation, it is understood that the second subscript is the ground. Hence, in this case, the voltage is measured with respect to ground. Capital letters with capital subscripts are used for DC values. For example, capital V subscript capital B represents the DC voltage at the node with respect to ground. VBP represents the DC voltage at B with respect to P. If VBP is positive, then VPB is negative. Capital letters with repeated capital subscripts represent power supply. That is, VCC is the power supply connected to the collector of a BJT. Small letters with small subscript represents AC or instantaneous values. And small letters with capital subscripts represents the total value, that is the DC value plus the AC value. So before we discuss operational amplifiers, since operational amplifiers are voltage amplifiers, let us review some concepts about voltage amplifiers. The two-port network representation of a voltage amplifier is shown in figure. Here, the part of the figure in the shaded portion is the amplifier equivalent circuit and the other components are connected externally. We have a source with source resistance Rs and a load resistance RL connected to the output. Our aim is to find the gain of the amplifier VO by Vs and the conditions under which the gain is maximum. For that, we first calculate Vi, which is the voltage across the input resistance of the amplifier and is given by Vs into Ri by Ri plus Rs by using the potential divider rule. Similarly, the output voltage VO equals AVI into RL by RL plus RO by a potential divider rule, and we know VI is Vs into Ri by Ri plus Rs. Substituting for Vi from the previous equation, we get this equation as A into Vs into Ri by Ri plus Rs into RL by RL plus RO. So the gain of the amplifier is VO divided by Vs given by A into Ri by Ri plus Rs into RL by RL plus RO. This is the expression for voltage gain of a voltage amplifier. In this expression, if Ri is infinity and RO is 0, then the amplifier will have the maximum gain given by AV equal to A. So, for an ideal operational amplifier, ideal voltage amplifier, Ri is equal to infinity and RO is equal to 0. So, ideal voltage amplifier will have infinite input resistance and 0 output resistance. An operational amplifier also is a voltage amplifier with extremely high gain. It amplifies the difference between two inputs rather than a single input. The inputs are inverting input marked minus and the non-inverting input marked plus. Operational amplifier is an integrated circuit which has two input leads, the inverting input and the non-inverting input. There is no explicit ground pin for an operational amplifier. Ground reference is established externally by power supply common. So this figure shows the symbol of an operational amplifier with the power supplies connected. The symbol resembles an arrow which indicates the direction of signal flow. And you have two power supplies, one positive supply connected to one lead and one negative supply connected to another lead. So usually operational amplifiers are working by dual power supplies like VCC and VE here. Typical value for the 741 type operational amplifier for the power supplies is plus and minus 15 volts or plus and minus 12 volts and so on. The voltages Vn at the inverting lead, Vp at the non-inverting lead and Vo at the output lead all are measured with respect to ground. In a practical operational amplifier circuit, the power supply connections are not explicitly shown. It is understood that the operational amplifiers are powered. This figure shows the schematic of a practical operational amplifier. There are three important parameters for a practical operational amplifier or any operational amplifier. RD is the differential input resistance, RO is the output resistance, and A is the open loop voltage gain. Open loop voltage gain is the voltage gain obtained when no feedback is connected. Usually in some circuits there will be feedback connected, then the gain is a closed loop voltage gain. For a practical operational amplifier, these values RD, RO and A are finite and non-zero. Typically for the MUA741 operational amplifier, RD is 2 mega ohms, RO equal to 75 ohms and A is 200,000 volts per volt, a very high gain. The differential input is defined as, differential input is Vd. The operational amplifier amplifies the differential input or difference between two inputs. The differential input is defined as Vp minus Vn. The amplifier amplifies this difference to produce an output. The output is given by AVD. You have a control source here. This is equal to, substituting for Vd, this equation becomes, this is A into Vp minus Vn. Now since Vo is equal to AVD, the output is given by AVD, you can express Vd, the differential input, in terms of output voltage and gain as Vo divided by A. So if A is extremely high, as A tends to infinity, you can see that Vd tends to 0. So for 741, you can see that the gain is 200,000. For more better amplifiers, the gain is still higher than this. So as A tends to infinity, Vd tends to 0. The differential input approaches 0. This is important. This have very serious consequences. We will come to that. An ideal operational amplifier is schematically shown here. It has the input resistance Rd equals infinity. So the input resistance is an open circuit. The output resistance is equal to 0. It's a short circuit. The open loop gain A is equal to infinity, and the currents IN and IP are 0. There is no current to either input of the operational amplifier. These are the ideal parameters. So the gain A is infinitely high, and from the previous slide we have seen that if A is very high, the differential input is approaching 0. So Vd equals limit A tends to infinity, Vo by A, that tends to 0. And we know that the operational amplifier is amplifying Vd, the differential input, to produce an output. And this expression shows that Vd is tending to 0. So it appears that the operational amplifier is amplifying 0 volts to produce a finite output voltage. This is not true. Indeed, Vd tends to 0 as A tends to infinity, but in such a way as to keep AVD non-zero. We will see how the op-amp achieves this in the next few pages. For that, we consider the inverting amplifier using an operational amplifier. This is the circuit diagram of an inverting amplifier. You can see a feedback connection from output to the inverting terminal of the operational amplifier. The output is fed back to the inverting input through a resistance RF called the feedback resistance. Since the output is connected to the inverting input or the minus input or the negative input, this type of feedback is called a negative feedback. If the connection is from output to the non-inverting input or the positive input, it is called a positive feedback. Amplifiers employ negative feedback in general. The operational amplifier is assumed to be ideal, which means that it has very high infinite input resistance, zero output resistance, and infinite open loop gain. The resistance Ri may include source resistance. The non-inverting input is grounded, and the op-amp power inputs are not explicitly shown. Understand that the operational amplifier is powered with dual power supplies plus V and minus V. So when a negative feedback is connected, we have seen from the previous slides that since the gain is infinitely high, Vd must be 0. Vp minus Vn must be 0. So when a negative feedback is connected, the operational amplifier will try to make the potential difference between inverting and non-inverting inputs 0. How will it do it? It generates such an output voltage which, when fed back to the inverting input, will make the potential at the inverting terminal equal to that at the non-inverting terminal. So by producing an output, it will make Vn is equal to Vp. The output is fed back to Vn, that will make Vn is equal to Vp. We say that there is a virtual ground connected at the inverting terminal. At this point, we assume that there is a virtual ground, or more correctly, a virtual short between Vn and Vp. There is no physical short, but there is a virtual short, which means that Vn and Vp are equal. A virtual ground means that whatever voltage is at the non-inverting terminal will automatically appear on the inverting terminal. This will happen only when a negative feedback is connected. A virtual ground does not draw any current. Only the voltages are equal. There is no current flowing between Vn and Vp. There are some more points we have to discuss on virtual ground. Virtual ground, as we have seen, means whatever voltage is at the non-inverting terminal will automatically appear on the inverting terminal. This means the inverting terminal tracks the non-inverting terminal with respect to voltage. The inverse of this statement is not true. That is, the non-inverting terminal does not track the inverting terminal. Virtual ground occurs only when a negative feedback is connected. A virtual ground will not draw any current. That is, the point is at ground for voltages but is open for currents. A virtual ground is also called a virtual short since the effect is shorting the inverting and non-inverting terminals. We come back to our inverting amplifier. Let us analyze the circuit. Analyzing, what we have is, since Vp is equal to 0, Vn also must be equal to 0 because of virtual ground. So the voltage at N is equal to 0. Since the voltage at N is equal to 0, the input voltage is entirely dropping across the resistance Ri, resulting in a current I is given by Vi by Ri. This current entering at this node cannot go into the input of the operational amplifier. Since this is an ideal operational amplifier, input resistance is infinite. This current completely flows through the resistance Rf, developing a voltage across Rf. The polarity of the voltage is as shown. So this is the direction in which the current flows. The output voltage is the voltage at the output terminal with respect to ground. This point and ground. And we know Rf is effectively connected between output and ground because this is virtual ground for voltages. So the output voltage is minus Vf, which means this is equal to minus I into Rf, and I is given by Vi by Ri, so we can write this as minus Vi by Ri into Rf. So the closed loop gain of the inverting amplifier is, now the gain is called a closed loop gain because there is a feedback. The gain of the amplifier with feedback. We have seen that the gain of the amplifier without feedback is infinite. That is open loop gain. But the closed loop gain is given by this expression. Vo by Vi is the gain which is equal to minus Rf by Ri. That is not infinite, it is finite. There is a negative sign which indicates that the amplifier is an inverting amplifier. The input resistance is equal to Ri. Input voltage divided by input current is input resistance, and the output resistance is 0 because it is an ideal operational amplifier. Some comments are worth noting about the inverting amplifier. The first point is, the gain of the amplifier is set by the ratio of two resistors rather than individual values. Such ratiometric values are more accurate and stable than absolute values. Hence, the gain is accurate and stable. Why ratiometric values are more accurate or stable? Suppose the temperature increases, the resistance also will slightly increase. Now, since the gain is the ratio of two resistors, Rf by Ri, the effect of temperature is the same for both the resistances if they are approximately in the same range. So that change in these values will be cancelled out. So the gain remains constant. Designing an amplifier of any desired gain is very simple. Simply decide two resistors. You need not know the internal architecture of the operational amplifier. This is why operational amplifiers are very popular. Designing an amplifier of any desired gain and any desired input resistance is very simple. Simply calculate the value of two resistors. Now, how is the operational amplifier making Vd 0? Assume that Vi is positive. So the voltage at N tends to be positive. So the operational amplifier will have to generate a negative voltage which when fed back to N becomes Vn is equal to Vp or makes Vn is equal to Vp. This is what the operational amplifier is doing when a negative feedback is connected. So it produces a negative output for positive inputs. Then only the voltage can be cancelled. Since it produces a negative output for positive inputs, it is called an inverting amplifier. So far we have seen that the operational amplifier has an open loop gain infinity. What will happen to the expression for the gain if the open loop gain is not infinite, it is finite? Otherwise, for all the other parameters, the operational amplifier is assumed to be ideal. RD is infinite, RO equal to 0, only the gain is finite. So if the gain is finite, we know the differential input VD is equal to VO divided by A. We know it. Now since Vp is equal to 0 because it is grounded, Vn must be equal to minus VO by A. So the voltage at this point is minus VO by A. Now apply Kirchhoff's current law at this node. The current entering must be equal to the current leaving. We get this expression Vi minus VO by A by Ri equal to minus VO by A minus VO by Rf. Algebraically simplifying this expression and taking the ratio VO by Vi, we get gain is equal to minus Rf by Ri by 1 plus Rf by Ri by A. So this is the actual expression for the voltage gain. In this expression, if A is tending to infinity or A is equal to infinity, the gain becomes minus Rf by Ri, because if A is infinity, the denominator becomes 1. That is the advantage of having very high gain. When we have very high gain, the expression for the gain is a simple one. Designing an amplifier is a very simple task. So we know for ideal operational amplifiers A is infinity, but we know for practical operational amplifiers the gain is extremely high but not infinity. We will see the consequences later. Now we will find an application for the inverting amplifier, the weighted summer or the summing amplifier. Circuit diagram shows a summing amplifier. Here n voltage sources V1, V2, V3, etc. Vn are connected to the inverting input of the amplifier through n resistors R1, R2, etc. Rn. Since n is at virtual ground, this point is at virtual ground, we can calculate the current I1 as V1 by R1, I2 as V2 by R2, and since this point is a ground point, you can add all these currents to become the current I. So this point is called a summing point for the currents. So I is equal to I1 plus I2 plus etc. plus In, which is equal to V1 by R1 plus V2 by R2 plus etc. plus Vn by Rn. VO equal to minus I into Rf, which is equal to minus Rf by R1 V1 plus Rf by R2 V2 plus etc. plus Rf by Rn Vn. So the output is the weighted sum of inputs. Inputs are weighted by resistance ratios and then summed. V1 is weighted by Rf by R1, V2 is weighted by Rf by R2 plus etc. plus Vn is weighted by Rf by Rn. That is why it is called a weighted summer. Inputs are weighted by resistance ratios and then summed up. Now if we put R1 equal to R2 equal to etc. equal to Rn equal to say R, then the expression for VO equals minus Rf by R into V1 plus V2 plus etc. plus Vn. So here, if all these resistors are equal, we get the output is proportional to the sum of the inputs. The sum is of course minus. If you want to get a positive sum, connect one more inverting amplifier to the output of this amplifier whose gain is equal to 1. Consider an example. Design an inverting operational amplifier circuit to form the weighted sum VO of two inputs V1 and V2. It is required that VO equals minus V1 plus 5 V2. The maximum output voltage should be 10 volt. The current in the feedback resistor should not exceed 1 mA. This is taken from reference 2. So looking at the question, it is clearly a problem of a weighted summer. The input V1 is weighted by 1, V2 is weighted by 5, gain is minus. So this is an inverting summing amplifier. The circuit diagram will be like this. You have two voltage sources and two resistors. And it is given that the output is 5 volt, the output is 10 volt, and when the output is 10 volt, the current through the feedback resistor should not exceed 1 mA. So given that VO equals 10 volt and I is equal to 1 milliamperes. So you can calculate RF from this expression. Because Vn is equal to 0, this output voltage is voltage across RF. Actually, it is minus voltage across RF. So we can calculate RF equals 10 volt divided by 1 milliamperes, which is equal to 10 kilo ohm. Now we know the weight of V1 is 1 and that of V2 is 5. So RF by R1 is equal to 1 and RF by R2 equal to 5. Solving, we will get R1 equals 10 kilo ohms and R2 equals 2 kilo ohms. That completes our solution. Consider another example. A circuit is given. Find Vn, Vp, Vo for the circuit. Vn, Vp and Vo. Also find power released by the 4 volt source. This is taken from reference 1. Here, a 4 volt source is in the feedback path. Negative feedback is provided by or provided through a 4 volt source. There is also a positive feedback connected here. So you can calculate Vp by applying the potential divider rule consisting of VO, 20 kilo ohm and 30 kilo ohm resistance. So the voltage Vp is equal to the voltage across the 30 kilo ohm resistance, which is given by VO into 30 by 30 plus 20. All resistors are in kilo ohms. So we get 0.6 VO as Vp. Since there is a negative feedback, Vn is at virtual ground. So Vn also must be equal to 0.6 VO. Now, if you apply the potential rule, we have VO minus Vn must be equal to 4 volt. So we have VO minus Vn is equal to 4 volt, which is equal to, which means VO equals 0.6 VO equal to 4. So that will give VO is equal to 10 volt. The output voltage is 10. Now since VO is equal to 10 volt, substituting in this expression we will get Vp is equal to 6 volt. And similarly, Vn also is equal to 6 volt. So we have our solution. Vn is equal to 6 volt, Vp equal to 6 volt and Vo is equal to 10 volts. What remains is to find the power released by the 4 volt source. Power released by the 4 volt source is the voltage 4 volt multiplied by the current supplied by the source. So let us calculate the current. Since this point is at a voltage of 6, there is a current flowing in this direction. The current through the 10 kilo ohm resistance is Vn by 10 equal to 0.6 milliamperes in the direction shown. This is the same current through the feedback path, which is through the voltage source. And now you can see that the current enters the positive lead of the voltage source. So the power is not released by the 4-volt source, but the power is consumed. So if you are asked power released by the source, it must be negative. So the power released by the source is equal to minus I into V, which is equal to minus 0.6 mA into 4 volt minus 2.4 milliwatt. So this is our solution. Vp equals 6 volt, Vn equal to 6 volt, Vo equals 10 volts, and P is minus 2.4 milliwatt. Now consider another example. A circuit is given. Find Vn, Vp, Vo. The operational amplifier is given to be ideal. This also is taken from reference 1. So here you have a current source of 1 milliampere is connected to the input. This is our connection diagram. A current of 1 mA is circulating around the circuit as indicated. This is the direction through which the current flows. When a current of 1 milliampere flows through 1 kilo ohm resistance, there is a 1 volt developed across the 1 kilo ohm resistance with the right side positive and the left side negative. Vp is then the minus the voltage across the 1 kilo ohm resistance. Vp is the voltage at this point with respect to ground, which is minus the voltage. So you can calculate that value first. Vp is minus the voltage across 1 kilo ohm resistance, or the voltage across 1 kilo ohm resistance with respect to ground, which is equal to minus 1 volt. And since there is virtual ground, Vn is equal to minus 1 volt. So we have Vp equals minus 1 and Vn equal to minus 1, and a 1 milliampere current is flowing through the 4 kilo ohm resistance. If a 1 milliampere current is flowing through 4 kilo ohm resistance, 4 kilo ohm into 1 milliampere, 4 volt is developed across the 4 kilo ohm resistance with the left side positive and right side negative. So Vo must be equal to the voltage across 4 kilo ohm resistance, of course, minus voltage across this plus the voltage at this node. So Vo is the voltage across 4 kilo ohm resistance plus Vn, which is equal to minus 4 plus minus 1 volt is minus 5 volt. So this is our solution. Vn is equal to minus 1 volt, Vp equal to minus 1 volt, Vo equals minus 5 volt. Now consider another example. This is the previous circuit itself, except that there is a 5 kilo ohm resistance connected across the node pairs A, B. In example 3, if a 5 kilo ohm resistance is connected across node A and B, find Vn, Vp and Vo. So it is exactly the same problem with a 5 kilo ohm resistance connected. The same 1 milliampere current source is connected, the other resistors are equal. So to solve this, first we have to convert the current source into a voltage source by using source transformation techniques. So instead of the current source, you have to connect a voltage source here. What should be the value of that voltage source? It must be equal to 5 kilo ohm into 1 mA, which is 5 volt. And this 5 kilo ohm is connected in series rather than in parallel. So by source transformation, the circuit becomes like this. A 5 volt voltage source and a 5 kilo ohm are added to this. Now, consider this loop. The loop consisting of 2 kilo ohm resistance, the plus 5 volt, the 5 volt source, 5 kilo ohm resistance, 3 kilo ohm resistance, Vn and Vp. Since there is a virtual short between Vn and Vp, this point and this point are at the same potential. So the voltage across this lead is equal to 0. So as far as voltage is concerned, you can consider this as a closed loop and you can apply Kirchhoff's voltage law. Remember that the current is not flowing through this path because there is no actual short circuit here. This is only a virtual short. But you can apply Kirchhoff's voltage law because there is a loop with respect to voltages. So applying KVL around that loop, we get V1 plus V2 plus V3 plus 0 equal to 5 volt. V1 is the voltage across a 2 kilo ohm resistance. V2 is the voltage across a 5 kilo ohm resistance. V3 is the voltage across 3 kilo ohm resistance. 0 is the voltage across these terminals. So it must be equal to 5. V1 plus V2 plus V3 plus 0 equal to 5. Now, if a current I is flowing through these resistors, the current will be the same through all the resistors. The voltage across 2 kilo ohm resistance V1 is equal to I into 2 kilo ohms. So, if there is a current I, then we say that I into 2 plus 5 plus 3 equal to 5. I is in milliamperes and R is in kilo ohms. That means 10I is equal to 5 or I is equal to 0.5 milliamperes. So the current through these resistors is 0.5 milliamperes. And we know that there is no actual current flow around the loop. So what is the actual path of the current? The current is not coming from here. The current is flowing in this path. This is the actual path of the current. A 0.5 milliampere passing through 1 kilo ohm, 2 kilo ohm voltage source, 5 kilo ohm, 3 kilo ohm, 4 kilo ohm and the output resistance of the amplifier. When a 0.5 milliampere of current is flowing through a 1 kilo ohm resistance, a voltage across the resistance formed will be 0.5 volt, 0.5 mA into 1 kilo ohm, with the right side positive with respect to the left side. The voltage at point P is the voltage across a 1 kilo ohm resistance with respect to ground. The voltage at P with respect to ground will be minus the voltage across the 1 kilo ohm resistance, which is equal to minus 0.5 volt. So Vp is the voltage across the 1 kilo ohm resistance, which is equal to minus 0.5 volt. And since there is virtual ground, Vn also is equal to minus 0.5 volt. So as in the previous case, you can calculate Vo equal to minus the voltage across a 4 kilo ohm resistance plus Vn. There is a current of 0.5 milliampere flowing through 4 kilo ohm resistance, which will develop a voltage of 2 volts across this. This is the left side positive and right side negative. So the output voltage is equal to minus 2 plus minus 0.5, which is minus 2.5 volts. So this is the result. Vn equal to minus 0.5, Vp equals minus 0.5 and Vo is minus 2.5 volts. Now, if you connect a T network or a T attenuator in the feedback path, what will happen to the gain? This is what we are investigating in this topic. Look at the circuit diagram. In the feedback path, you have three resistors R2, R3 and R4 connected as shown. Vn is equal to 0 volt because of virtual ground. Since Vn is equal to 0, we can calculate Ri1, which is equal to Vi by R1. This same value of I1 flows through this path. The current to the input of the operational amplifier is 0. So I1 must be equal to I2, which also is equal to Vi by R1. Now, what will be the voltage at this point? Voltage at this point is equal to 0 volt minus the drop across R2. Drop across R2 is I2 into R2. So it is 0 minus I2 R2, which is equal to minus I2 R2. And we have I2 is equal to Vi by R1. Substituting that, we get this is equal to minus R2 by R1 into Vi. Now that we know the voltage at this node, you can calculate the current I3. I3 is equal to the current through the resistance R3, which is equal to the potential difference across R3 divided by R3. So we will calculate R3 as VQ divided by R3. We have VQ given by this expression minus R2 by R1 into Vi by R3. So that expression becomes minus R2 by R1 R3 into Vi. So this equation indicates that I3 is opposite to the direction indicated. I3 is approaching the node rather than moving away from the node. Now, if you apply Kirchhoff's current law at this node, the current entering must be equal to current leaving. So I2 must be equal to I3 plus I4, or I4 is equal to I2 minus I3. We know these values. I3 is known, I2 is known. So you can calculate that. That will be equal to minus Vi by R1 plus R2 by R1 R3 into Vi. And once we know I4, we know the voltage across R4. And once we know the voltage across R4, the output voltage is equal to the voltage at Q minus the drop across R4. Output voltage is equal to voltage at Q minus the voltage across R4. So the output voltage VO is equal to VQ minus I4 into R4. We know the expression for VQ. We know the expression for R4, I4. So substituting these values, we will be getting an expression like this. You can note that the value of I4 is independent of the value of R4. This point is important. So what remains is to simplify these expressions. We can simplify it like this. Finally, the gain will be equal to minus R2 by R1 into 1 plus R4 by R2 plus R4 by R3. Is there any advantage in connecting a T network in the feedback path? Let us see a problem. Design an inverting amplifier with T network in the feedback. The input resistance should be 500 kilo ohms. The gain required is minus 80. Do not use resistors greater than 500 kilo ohms. This is taken from reference 3. So it is an inverting amplifier with T network connected. It is given that the input resistance is 500 kilo ohms. Input resistance is R1 because it is an inverting amplifier. So you have to choose R1 to be equal to 500 kilo ohms. Now once we choose 500 kilo ohm, we have to choose the maximum value for R2 because this factor should not be less than 1, should be greater than 1 because the gain required is 80. So the maximum value that you can choose for R2 is restricted by 500 kilo ohms. Do not use resistors greater than 500 kilo ohms. So make R2 also is equal to 500 kilo ohms, which will make the first term R2 by R1 is equal to 1. So we have R2 also is equal to 500 kilo ohms. It cannot be less than that. And it cannot be greater than that also because of the restriction given in the question. So our conclusion is the second term 1 plus R4 by R2 plus R4 by R3 must be equal to 80. 1 plus R4 by R2 plus R4 by R3 must be equal to 80. This term is 1. So the gain is decided by these parameters. And we already know R2 is equal to 500 kilo ohms. So it is desirable to have this term more than 1 or at least 1. So the maximum value that R4 can take also is equal to 500 kilo ohms. It cannot be less than that. It cannot be greater than that. Given the condition that resistance should not be greater than 500 kilo ohms. So by this argument, you choose R4 also equal to 500 kilo ohms. So what remains is to find R3 alone. So it is R3 alone which decides the other parameter. So if R4 is equal to 500, R2 equals 500, we have 1 plus R4 by R3 equals 80. That is 2 plus R4 by R3 equals 80, or R4 by R3 is equal to 78. Simplifying, we will get R3 equals 6.41 kilo ohms. This completes our design. Now, what is the advantage of this type of connection? Consider or assume that you are required to set up an amplifier whose input resistance is 500 kilo ohms and gain is minus 80. If you were using a single feedback resistance RF to get a gain 80 and an input resistance 500, you require RF equal to 500 kilo ohms into 80, which is 40 mega ohms, an impractically high value. So if you are using this type of network, this T network, it is possible to use practical values, or it is possible to avoid impractically high values in the circuit. Not only that, when we study the non-idealities of operational amplifiers, we will see that even if say 40 mega ohm is available, you are not recommended to connect it in the feedback path because of the non-ideal behavior of the operational amplifier. We will come to that later. How is this possible, or how is the T network achieves this goal of reducing the feedback resistance, keeping input resistance unaffected? So you can see that since virtual ground is there, the point Vn is 0, and since Vn is equal to 0, R2 and R3 are effectively in parallel. If there is a parallel combination of two resistors, the current is mainly decided by the lower value because the effective combination will be lesser than the lower value. So if you purposely reduce R3, you can pump more current into R3, which eventually will send more current through R4. Assume that we make R3 smaller by a factor by say K. Then we are pumping more current into R3 by the factor K. So the current, if K is K times, you are making the resistance R3 K times smaller, the current through this resistance will be KI1, and the current through R4 will be K plus 1 I1, which is higher than these currents. And the current through R4 is independent to the value of R4. So this high current will develop a high voltage across R4, which in turn will make a high voltage in the output. So we have this advantage when you are using T network in the feedback path. You can avoid extremely high resistances to get a desired gain and desired input resistance. So we stop our discussion here. These are the references used in this lecture. And thank you. We will meet again with another lecture.